The following is a presentation of various problems in number theory. Problem 1.2. What are the possible remainders when a perfect square is divided by 3, or by 5, or by 6? Well, the representations here show that n for mod 3, representing the integers, would be 3q plus some remainder r. And when we square it, we'll FOIL out, and we get 9q squared plus 6qr plus r squared. Well, what we're really concerned with here is only the r squared term, because 9q squared will definitely be divisible by 3, and 6qr will be divisible by 3. 6 divided by 3 is 2. And so what we do is we just take each of the congruence classes in mod 3, 0, 1, and 2, and we square them and see where the squares lie in mod 3. So for example, if I have 6 and I square it in mod 3, I have 36. Well, that'll be 0 mod 3, so the remainder will be 0. If I take the number 7, well, 7 squared is 49. Well, 48 is divisible by 3, so it's 1 more. So the remainder is 1. And also, if I take a number that's in 2 mod 3 and square it, such as 8, well, 8 squared is 64. That is also 1 in mod 3. So the only possible remainders are 0 and 1. If you follow this rule, just take the congruence classes and square each one, you'll find the same results on the table below for mods 5 and 6. The remainders in mod 5 are 0, 1, and 4, and the remainders in mod 6 are 0, 1, 3, and 4. Problem 1.5. Calculate the greatest common divisor of 1,485 and 1,745. Well, for this problem, we'll use the method described by Euclid in his Elements, Encyclopedia of Math, Book 7, from about 300 BC. And the following algorithm, the way it works is you take the larger number and then you represent that as the smaller number times a multiple plus a remainder. So here we'll have 1745 equals 1 times 1485 plus a remainder of 260. Then, just look at the right side here, we're going to take 1485 and represent that as a multiple of the remainder 260 plus a new remainder. So the second line we have 1,485 equals 5 times 260 plus 185. Repeating this, we'll have 260 now equals 1 times 185 plus a remainder of 75. Then 185 can be represented as 2 times 75 plus 35. 75 is 2 times the remainder of 35 plus 5. Then lastly, we have 35 equals 7 times 5 with no remainder. Therefore, the greatest common divisor is the last remainder of this process, which is in the second to last line, so the greatest common divisor is 5. Problem 1.6. Find a pair of integers u prime not equal to -5 and v prime not equal to 7, such that the greatest common divisor between 1,492 and 1,066 equals the linear combination 1492 u prime plus 1066 v prime. Well, we need to find first d, which is the greatest common divisor. We could use Euclid's algorithm, but actually here I did use the prime compositions. So if you look at the primes that make up 1492 and 1066, the greatest common divisor, the only factors they have in common is that one pair of 2's. Bouzoux's identity states that the greatest common divisor between A and B, that would be 2 in this example, will be some number times 1492 plus 1066 times some other number v. But they gave us a solution. They said that, well, one combination that works for this pair A and B are -5 and 7. So I wrote that on the table as the old solution. So to create a new solution, we do an interesting trick with the conjugate. So what I do is I'm going to shift u along the number line to the left, and I'll shift v on the number line to the right based on the gaps of 5 and 7 in a clever way. So I'll move u prime, I'll subtract 1066, so I'm subtracting b. And for v prime, I'll take that 7, but I'll add a, 1492. So the new numbers are actually negative 1071 and 1499. And what happens is, and you can check with the factoring in the paragraph below, is what we have are the new combination, 1492 times that new number, which I left as negative 5 minus 1066, plus 1066 times 7 plus 1492. Well, if you left factor in, it creates 4 terms, and you'll see that the second and the fourth terms are additive inverses. They'll cancel each other. So mathematically, this is the same value. The first and the third terms are what we had before in the old solution, which we already know is 2. So if you look down below, we'll have the exact same solution as before after the 2 terms cancel. So we can plug in 2 equals 1492 times negative 1071 plus 1066 times 1499, and we'll get the greatest common divisor, 2. Therefore, another solution to this system is u prime equals negative 1071 and v prime equals 1499. Problem 1.7. Express the greatest common divisor of 1485 and 1745 in the form 1485u plus 1745v. You can see that once again I've used Euclid's algorithm to solve for the greatest common divisor of these two numbers, a and b, which is 5. That is shown by the line 75 equals 2 times 35 plus 5. That remainder is the greatest common divisor. Well, to solve Buzot's identity, stating that this 5 equals AU plus BV, we're going to work with Euclid's algorithm in reverse. So starting with that second to last line, I'll solve for 5. And down below you'll see, well, 5 then equals 75 minus 2 times 35. Then, for the next line, I'll use the line above in the solution using Euclid's algorithm. So we know that 35 can be expressed as 185 minus 2 times 75. That's useful because now we have 2 larger factors, and if you distribute in the negative 2 and regroup, you have line 4, which is 5 equals negative 2 times 185 plus 5 times 75. Now that 75 can be expressed as the third line up above using Euclid's algorithm. 75 equals 260 minus 185. If you distribute again in the 5, repeating this process, and regroup, you'll get that 5 equals 2 times 260 minus 7 times 185. Just repeat this process going line by line, building up to the larger factors. And in the end, you'll have the original 2 factors of a and b, now with left factored u and v. And the last line is 5 equals 40 times 1745 minus 47 times 1485. Therefore, the solution u equals negative 47 and v equals 40 will satisfy this a and b. Problem 110. Find the greatest common divisor of 1082, 1155, and 2002. And as a second problem, find the greatest common divisor of 4 numbers, 910, 780, 286, and 195. Well, to solve this, we use a reiteration method for these groups of numbers. Basically, you just start on the far left, take the first 2 numbers, find the greatest common divisor, and then cross off those 2 numbers, write in that new d, and then repeat the process for the next 2 numbers. So let's see this for the first problem. So just start on the left with 1092 and 1155. And here I did not use Euclid's algorithm. I used prime decomposition. And looking at those lists, 1092 is the unique number that is 2 times 2 times 3 times 7 times 13. And 1155 is the unique number that is 3 times 5 times 7 times 11. And the only number that is on both lists are 3 and 7, so that's 21. cross off those two numbers, write in 21, and then we'll find the greatest common divisor between 21 and the last number, 2002. Well, 21 is 3 times 7, and 2002 is 2 times 7 times 11 times 13. So the greatest common divisor is 7. And we're done, because that was the whole group. So the greatest common divisor of 1092, 1155, and 2002 is 7. Repeating this process for the 4 group numbers here, 9, 10, 780, 286, and 195, start with the 2 numbers on the left. 9, 10, and 780 have a greatest common divisor of 130. Cross off those 2 numbers, find the greatest common divisor of 130 and 286. That would be 2 times 13, or 26. Cross off those 2 numbers, write in 26. Then find the greatest common divisor of 26 and 185, and you'll find that the GCD is 13. That means that the greatest common divisor of these 4 numbers, 9, 10, 780, 286, and 185, is the number 13.